Forward versus deferred rendering, the decision that defines your graphics budget. Hello and welcome to episode number 18 of the Unity Performance Task Force podcast. I'm your host Ruben from TheGameDev.Guru, and as usual I'll kick things off with a question for you. Have you ever heard someone say, use deferred rendering for better lighting, or forward rendering is faster on mobile, and thought to yourself, what does that even mean and how do I decide? Sounds familiar? If so, this episode is for you. Today we're talking about forward versus deferred rendering, and I see a lot of developers get scared when this topic comes up. They think it's super complicated, full of low-level graphics programming they'll never understand. But here's the truth. At a high level, this decision is actually quite simple. And by the end of this episode, you'll have a clear strategy for choosing the right rendering path for your project. So let's start with the basics. What is a rendering path? A rendering path is just the strategy that the CPU tells the GPU to use when rendering a frame. It's the sequence of steps the GPU follows to take your 3D scene and turn it into a 2D image on the screen. Different paths have different trade-offs. Some are faster, some use less memory, some handle real-time lighting better. And you, as the developer, get to choose which path Unity uses. If you don't choose, Unity picks for you based on defaults. But that choice has a huge impact on performance, which ultimately affects your graphics fidelity. If you can't pay the performance cost of one rendering path, you might have to drop visual features to hit your frame rate target. So this decision matters. There are two main rendering paths, forward rendering and deferred rendering. Let's break down how each one works. Forward rendering is the simpler of the two. The render loop has three main steps. First, you clear the buffers. At the start of a new frame, you want a clean slate, so you clear the color buffer, the depth buffer, the stencil buffer, whatever you need. You're starting fresh. Second, you loop through every renderer in your scene and submit it to the GPU. For each object, you run the full pipeline. The vertex shader transforms the vertices. The fragment shader calculates the final color, including all the lighting, everything. When that object finishes rendering, it's done. It's fully lit and drawn onto the back buffer. You move on to the next object and do the same thing. Third, once every renderer is drawn, you swap the front and back buffers. What you drew on the back buffer is now visible on the monitor. The other buffer becomes the new back buffer for the next frame. That's it. Clear, draw everything with full lighting, present the image. Simple. Let me show you what this looks like in RenderDoc. I set my Unity camera to forward rendering, captured a frame, and here's what I see. At the start, there's a clear operation. Depth buffer, stencil buffer, color buffer, all cleared. Then I see a section labeled Render Forward. As I scrub through the draw calls, I can watch the scene being built up piece by piece. And here's the key thing. Every object is already fully lit when it's drawn. The lighting calculations are done right there in the fragment shader. So as each object appears, it looks final. No intermediate steps. Just the finished result going straight into the back buffer. This is the beauty of forward rendering. It's straightforward. For each object, you do all the work and then you're done. But it also means that if you have a lot of real-time lights, your shaders get more complex. In URP, every additional light adds more work to the fragment shader because it loops through all the lights and accumulates their contributions. In the built-in render pipeline, each additional light can potentially add more draw calls. Either way, it doesn't scale well past 2 or 3 real-time lights. Now let's talk about deferred rendering. This approach is more complex, but the idea is to delay the lighting calculations as long as possible. Instead of rendering each object fully and immediately, you split the work into two phases. Phase 1, render all the geometric information you need into multiple buffers called G-buffers. G-buffers stands for geometric buffers. These buffers store things like world space position, world space normals, albedo color, specular values, smoothness, occlusion, whatever you need for lighting. Each object gets rendered, but instead of outputting a final lit color, it outputs this data into the G buffers. So you might have one buffer for albedo, another for normals, another for specular, and so on. Phase 2. Once all opaque objects are rendered into the G buffers, you combine that information to calculate lighting. You do this in a separate pass. At this point, you have complete information about the scene. You know the position, normal, and material properties of every visible pixel, so you can apply all your lights efficiently in one go. This is why deferred rendering scales well with many real-time lights. You're not recalculating lighting for every object. You calculate it once, using the data from the G buffers. Phase 3. Semi-transparent objects can't be handled by deferred rendering because you're overwriting pixel data in the G buffers. Transparency requires blending multiple layers, and G buffers don't support that. So after the opaque pass and lighting, you switch back to forward rendering for any transparent objects. Finally, you present the image, swap buffers, and you're done. Let me show you this in RenderDoc. I switch my camera to deferred rendering, capture a frame, and open it up. Right away, I see multiple render target views being cleared. These are the G buffers. Then I see a section labeled Render Deferred G Buffer. As I scrub through the draw calls, I can see data being written to different buffers. One buffer shows world space normals, another shows albedo, another shows specular. The objects look flat and unlit at this stage because we haven't done the lighting calculations yet. Once all the opaque geometry is done, there's a lighting pass. Unity combines the G buffers and applies the lights. Now the image looks lit. After that, there's a forward rendering pass for transparent objects. And finally, the image is presented. Here's a concrete example. I look at one of the G buffers, render target 2, which stores world space normals. The colors look greenish and bluish, which is typical for normals encoded in RGB. Every draw call writes to this buffer. Another buffer, render target 0, stores albedo and occlusion. I find a plant in the scene, and when I inspect that draw call, I can see the albedo data. It's flat, no lighting, just the raw color from the texture. The lighting happens later in the deferred lighting pass. If you want to know exactly what each G buffer contains, check the Unity documentation for deferred shading. It lists the format and contents of each render target. Render target 0 is diffuse color and occlusion. Render target 2 is world space normals, and so on. This is all implementation specific, so it can change between Unity versions or render pipelines. So that's how the two rendering paths work. Now let's talk about the trade-offs. Forward rendering has a lot of benefits. It's simple. It uses minimal memory. You only need a color buffer, a depth buffer, and maybe a stencil buffer. That's it. This makes it great for mobile devices, where memory bandwidth is a huge constraint. The fewer bytes you have to transfer, the better your performance. But forward rendering has a big limitation. Lighting doesn't scale. If you're using the built-in render pipeline, each additional light can add more draw calls. If you're using URP, each additional light makes your fragment shaders more complex. On mobile, you're typically limited to 0 or 1 real-time light. Maybe 2 if you're lucky. Beyond that, performance falls off a cliff. Deferred rendering has different trade-offs. The big advantage is flexibility with real-time lighting. Because you calculate lighting in a separate pass after rendering all the geometry, adding more lights is much cheaper. You can have 5 lights, 10 lights, and performance scales reasonably well. Deferred rendering also gives you a lot of information about the frame. You have buffers for normals, albedo, specular, everything. This makes certain post-processing effects easier to implement. You have all the geometric data at your fingertips. But deferred rendering has serious downsides. First, memory usage. You need multiple G buffers and each one takes significant space. Let me show you how to estimate this. Say you're targeting Oculus Quest 2. The resolution per eye is 1832 by 1920. For stereo rendering, you multiply that by 2. So you create a render texture in Unity with those dimensions and check the memory usage at the bottom. It shows about 26 megabytes per buffer. That's just one buffer. If you have 4 or 5 G buffers, you're looking at over 100 megabytes just for those buffers. On a memory-constrained device like Quest, that's a huge cost. Second, memory bandwidth. On mobile GPUs, which use tile-based rendering, bandwidth is often your biggest bottleneck. Deferred rendering forces you to read and write these large G buffers constantly. I've seen projects on Quest spend 6 milliseconds of their frame budget just swapping between render targets. That's half your performance budget gone, just from memory traffic. It's brutal. Third, semi-transparency doesn't work in the deferred pass. You have to fall back to forward rendering for transparent objects, which adds complexity. Fourth, MSAA, multi-sample anti-aliasing, doesn't work with deferred rendering. You have to use other techniques like FXAA or TAA, which can be more expensive and don't always look as good. Fifth, you lose some flexibility. For example, the receive shadows flag on mesh renderers doesn't work in deferred mode. You also have limits on the number of culling masks you can use. All of this adds up to one conclusion. Deferred rendering is tough on mobile. The memory bandwidth cost alone can kill your performance. Very few mobile projects can afford it. So when should you use forward rendering and when should you use deferred rendering? Here's my simple decision framework. Use forward rendering if you're targeting mobile. Period. The memory bandwidth cost of deferred rendering is just too high. On Quest, on phones, on tablets, forward rendering is almost always the right choice. If you're targeting desktop or console, you have more flexibility. If you have 2 or fewer real-time lights, forward rendering is fine. 1 light is no problem. 2 lights, you might start to see some cost, but it's manageable. If you have 3 or more real-time lights, that's when you should seriously consider deferred rendering. At that point, the shader complexity or draw call count in forward rendering starts to hurt. Deferred rendering scales better with multiple lights, so it becomes the more efficient option. That's it. That's the decision tree. Mobile, forward. Desktop with 2 or fewer lights, forward. Desktop with 3 or more lights, consider deferred. One more thing. If you want to estimate the memory cost of your G buffers, here's a quick trick. Find the resolution of your target platform. For Quest 2, it's 1832 by 1920 per eye, times 2 for stereo. Create a render texture in Unity with that resolution. At the bottom of the inspector, Unity shows the memory size. That's roughly how much each G buffer will cost. Multiply that by the number of G buffers and you get the total memory footprint. This doesn't account for depth buffers or other details, but it's a good approximation. This is the exact framework we use at TheGameDev.Guru when advising teams on rendering paths. We look at the target platform, count the real-time lights, estimate memory cost, and make a recommendation. Takes about an hour to gather the data and run the numbers. Usually saves teams weeks of trial and error. Now let's talk about objections and edge cases. First, what if I need more lights on mobile? Use baked lighting or light maps. Pre-calculate as much as you can. Real-time lighting on mobile is expensive no matter what rendering path you use. Second, what if I'm on desktop but I still want forward rendering for some reason? Go for it. Forward rendering works fine on desktop. You might hit shader complexity limits with many lights, but for simpler scenes it's totally viable. Third, what if I want to switch rendering paths mid-project? You can, but test thoroughly. Shaders behave differently in forward versus deferred. Some features might break. Profile and compare before you commit. Here's your action plan. First, identify your target platform, mobile or desktop. That alone narrows your options. Second, count your real-time lights. Are you using 0, 1, 2 or more? Be honest. Don't count baked lights or light maps, only real-time. Third, if you're on mobile, choose forward rendering. Done. Fourth, if you're on desktop with 2 or fewer lights, choose forward rendering. Fifth, if you're on desktop with 3 or more lights, prototype both paths. Build a test scene with your actual content. Profile both forward and deferred. Measure frame time, memory usage, and visual quality. Then make a data-driven decision. Let's recap. A rendering path is the strategy the GPU uses to render a frame. Forward rendering is simple, uses little memory, and works great on mobile, but it doesn't scale well with many real-time lights. Deferred rendering scales better with lights and gives you more geometric data, but it uses a ton of memory and bandwidth, which makes it tough on mobile. Your decision comes down to platform and light count. Mobile, forward. Desktop with 2 or fewer lights, forward. Desktop with 3 or more lights, consider deferred. And remember, performance always dictates graphics fidelity. If you can't afford the cost of one rendering path, you'll have to cut visual features to hit your frame rate. If you found this podcast episode useful, you can access in-depth lessons in the Unity Performance Task Force program at www.performancetaskforce.com. And if Unity consulting is what you are after, book a free discovery call at https://consulting.thegamedev.guru. Till next time.